Okay, so good evening, students. This is Dr. John. I'm sorry for recording this video late. This is because on this Thursday, I just had a project like discussion and a meeting with a student. So that student is a master student who is doing cybersecurity research with me. He's doing his research project with me, and his topic is mainly intrusion detection. So we just tested some malwares together, and we want to collect the traces, the network traces of those malwares, in order for us to build a profile for the purpose of detection. But unfortunately, one of those malwares just say let my laptop down. So it totally crashed my laptop. It took me like 2 or 3 days to get my laptop back to normal and restore all the previous files. So I just received my MacBook my laptop this afternoon from the Apple Store. I just had to send it to them for them to do the backup for me, and fortunately I got almost everything back, and now I'm ready to record this video for you, and today we're going to enter the second part of our semester, of our course, so in which we're going to focus on data structures. So let's say let's say what is the difference between data structures and algorithms. So first, let's look at what is an algorithm. If you remember, in the first lecture, I said that what is an algorithm? An algorithm basically is a computational procedure to solve a problem. Okay, so it's a computational procedure. Okay, so let's say let's look at it in more details. So for example, if we go back to the previous sorting algorithms that we have learned together, so a sorting algorithm basically so takes an input, which is an array, and then it gives you an output, the desired output. This is the function of algorithm. Okay, so this is what an algorithm does. So giving certain input, it delivers the expected output. But what about data structures? So data structures, you can take it in this way. So data structures is a way for us to organize the input. It's a way for us to input. It's basically an input organizer or data organizer. Input or data organizer. So we want to organize the data in a way in which if we deliver that input or data to the algorithm, so the algorithm can solve the problem very efficiently. Okay, so let's from here probably you can see that structure is basically a container or organizer for us to organize the data, so that if we feed the data to an algorithm, the algorithm can deliver the output in a very efficient way. So actually, the algorithms and data structures, they interact with each other. They rely on each other in order to make our program execution more efficient. So that's why our course is talking about these two topics, data structures and algorithms. So okay, and next let's do a quick review of what we have learned. In the first part of our course, we basically focus on one particular kind of algorithms that is called sorting algorithms. So we actually learned 5 algorithms, sorting algorithms. We have insertion sort, merge sort, heap sort, quick sort, and accounting sort. So for heap sort, this is optional. Heap sort is optional. Because it relies on a data structure named heap. So I think so. The reason why I make it optional is because it's way more. It's too complicated, especially for us who just started to learn algorithms without any background of that structures. So that's why I said I make it optional. So if we look at these different algorithms, all of them take the input as an array and help us to sort the elements in the array. And basically these algorithms deliver different time complexity. We said in general or in practice, the most efficient one is quicksort. So as I said before, if you go to a job interview and if one of your programming interview questions is sorting algorithm, by default you should always go for quicksort. And then we also learn a version of sorting algorithm that is in theory more efficient than quicksort. That is called counting sort. So but counting sort has a big limitation. That is, so all the numbers in the array must be integers from 0 to k. So okay, so this is a review of the first part of our course, and then today we're going to learn three data structures. Stack and queue are in the first part. I'm going to talk about the other one named LinkedList in the second part. So what is stack and queue? Before talking about stack and queue, and I want to let's talk about the operations on array. Suppose here we have an array A, so with let's say four elements in it. Let's say 4, 3, 1, 2. Just for a quick example. Suppose now we want to insert a new value into the array. We want to insert 6. We want to insert 6 to the end of the array. How could we do that? So what we have to do is that we create another array whose size is 5. And then we need to copy and paste everything from the original array to the new array. And then copy the last element 6 into that. So how many operations did we do? So here we did 4 plus 1 operations. 4 is here we got 4 plus 1 copies. 4 copies from the 4 copies for the original values and 1 copy for the new value to be inserted. So let's be general. Okay, suppose that we have an array A whose size is not 4. Let's use n. In general, okay, how many operations do we need to perform? Then we will need n plus 1 operations. And if we use big O notation, this is the complexity would be big O n plus 1. And this is equivalent to big O n because we always want to ignore, we only want to keep the dominant part, the most significant part. So that's the reason why we eliminate the plus 1. So it is O n complexity. So which means this, okay, to insert a single element, in order for us to insert a single element into an array, the time complexity is O(n). It linearly is also the execution time linearly depends on the size of the array. So let's say if we have n equal to 1 million, let's say just we have an array with 1 million elements, and if we want to add a new value into that, then the time, so we have to do 1 million and plus 1 operations. That is too much. So this is not efficient. It's not efficient at all. So it's like if we want to add a new student into our course, we have to create. So we have to, let's, for example, if we have 30 students in our class, and if we want to add one more student into the class, that is, so the O(n) complexity is pretty much like we have to create a new classroom which can seat 31 students, and let all the original 30 students go to the new classroom, and then let the new student also go to the new classroom. This is way too much complicated. So here what I said is that the insertion and for array the insertion and the insertion complexity, insertion and also for deletion is the same. The deletion complexity are both on. So n is the size of the array, and this is too much. What do we want? So here, suppose here we have a list of elements for us to organize, and we have to do insertion and deletion very often. So we definitely need a data structure that can help with more efficient insertion and deletion operations. So that's why we are going to learn the three new data structures, which include stack, queue, and linked list. So these three data structures provide O1 complexity with insertion and deletion. So what is O1 complexity? So if we draw let's look at what's the difference between O1 complexity and O(n) complexity. So let's say we denote n on the x-axis, and then we denote the execution time on the y-axis. If to perform insertion and deletion to an array, so the execution time actually linearly grows with the size of the array. However, if we use stack and queue, the time complexity would remain flat. It will remain constant. So it is not relevant to, it is totally irrelevant to the size of so the number of elements. So let's say if we insert a new element into a list of maybe, let's say, 5 elements, if it takes 1 millisecond, then if we want to perform the same operation over another list which includes 1 million elements, the time would be the same. So that is what we want. So because we only so this complexity is going to be significantly lower than O(n) complexity. This is O(n) and this is O(1) complexity. And what we want is right over here. Okay, we want the time to be flat. Okay, or another way is like, you can take it as the number of new COVID cases. Let's say O(n) complexity is like with days go. If we take n as the number of days, so it's like with days going on, we will have more and more cases reported. But O(1) complexity is like a flat curve. So every day we have the same number of infected cases, and this is what we want. We want to flat. At least we want the curve to be flat. Otherwise, we are going to go through another pandemic or another hell again. So which is very likely, unfortunately. So probably some of you already noticed that in France, in some European countries, the second wave is coming, and it's coming sooner than most people expected. Originally, the scientists expect that the second wave to arrive in late October, but it seems that it arrives in either like late September or early October. So hopefully, so this time the U.S. is going to do a better job, but I highly doubt. So I'm going to talk about that later. Okay. So let's look at the stack and queue. So stack and queue are two dynamic sets. They're based on arrays. So the fundamental of them are still arrays, but they provide different operations. So the main difference between stack and queue is that so stack implements a last in first out policy, while queue implements a first in first out policy. This may sound like what very abstract or very strange for you, but I'm going to talk about that in a more understandable way. So for example, let's look at this one first. Last in first out. Okay, let's talk about last in first out. So here, suppose that we have a shelf. We have a shelf in a wholesale market. Let's, for example, at Costco. Originally it is empty. Suppose that you are a employee at Costco, and there you need to put so let's say 4 packs of water on the shelf. So what you are going to do is that, so you are going to put the first pack at the bottom, and then the second pack on top of it, the third pack on top of it, and the last pack on top of that, right? So it's like the so whichever comes later, which pack that comes later will be on top, will be on the top. The pack that arrives the latest will be at the top. So here let's consider different roles. Suppose that you are a customer and you come to Costco, so and you want to buy a pack of water. Just suppose that all these you just say these 4 packs of water, and all of them are in good shape. So which one are you going to get? So I think, without any doubt, most people will get the top pack, right? So very few people will just remove the first 3 pack. Very few people will just remove the first 3 pack, and then get the bottom pack. No, so I think 99% of the people will go for the top pack. Okay, so what you see is that the pack that arrives at the shelf at last will be removed first. That is called last in, first out. That is called last in, first. Whoever comes last will be removed first, will go out first. That is called last in, first out. Or you can think of last in, first out as a single-ended tube. So let's say we just got some balls into the tube, and then the ball that will go out of the tube first is the ball that arrives the latest. So again, it is last in, first out. So then let's look at what is first in, first out. First in, first out is like, suppose here you come to visit your family doctor, and there are, let's say, 5 chairs in your family doctor. There are 5 chairs in your family doctor's waiting room. So we have patient A, B. So A arrives first, and then B, and C, D, E. So they just sit in a sequence. So who is going to see the doctor first? It's A. So it's like whoever comes first will be able to go out or go to see the doctor first. So this is called first in, first out. So Q implements the first in, first out policy, while stack implements the last in, first out policy. So you can take Q as a double-ended tube. So we have the fluid going over this way. Okay, so the drop that comes first will be able to get out of the tube first. So this is the first in, first out policy. And so first let's look at, okay, how can we implement stack? And actually, as I told you before, both stack and queue are based on arrays, but they are just variations of array. They provide an alternation on the array. So let's say, so the limitation, the main problem of array is that we leave no buffer space. So suppose if we originally, if we want to store 4 elements in the array, we just create a space of 4 and let all of them be occupied. Okay, so that's the main problem. So if we want to add a new element to the array, there is no empty space available. So we have to create a bigger array and copy and paste everything to it. So here, stack operates array in a different way. So so in stack, what we do is that we usually create a stack of a much larger space than we actually need, than what we actually need in the first place, and we only let's say the first 3 or 4 of them be occupied, and then if we want to add a new element into that, we just place the new element, let's say the new element, into the first available place. Okay, so this is the difference between stack and array. Stack is like an array with buffer space, and So here and we use, so suppose here we create a stack with 7 space. Right over here we create a stack with 7 space, and and originally we have 4 elements in that. So we are going to use an attribute value named top to denote, okay, which one which one is the last value in the array. So if here we have top equals to 4 because at the position 4 we have the last element. So here by through this value we know, okay, so how many elements are stored in the array. We know that the first 4 spaces are occupied. Okay, so this is stack. Stack, as I said before, stack is an array with buffer space, and also it uses an additional variable named top to denote, so where is the last value. Okay, first let's say how do we check if the stack is empty or not. So here, if we have a stack that is totally empty, so with no elements in that, where should we place top? Okay, some of you may say we should place top right over here at the position 1. But actually no, if you place top at 1, it gives you people an illusion saying that, okay, so so we have the last element is at this place, meaning that we have a value right over here. But actually no, there is no value over here. So instead of setting top as 1, we should put top as this 0. Okay, top as 0. So when you create a new stack, initially we also have top as 0. It denotes that there is no element in this stack. So to check if the stack is empty or not, it's very simple. We just need to check if it's 0 or not. If it's 0, we return true. Otherwise, we return false. So this is the function for us to check if the stack is empty or not. And then, so let's look at the second function called push. Push is like insertion. So we give it a special name. We give stack a special name called push. It's for the purpose of insertion. And so push takes 2 parameters, input parameters s, which is a stack. S is the stack, and x is the new value to be pushed into the stack. So let's look at over here. Okay, suppose here we have a stack, and we want to insert a new element or push a new element. X equal to, let's say 17 into the stack. Where are we going to place that? Where are we going to place the new value? So of course we need to place it right over here, right? So we need to place it at this place, put it at this place. So this is pretty much like if we have a shelf with 7 spaces available, and what we know is that the last space, so this top points to here, so it's like we know that the last pack is over here with the above spaces available. So we're going, so if you are the employee working at Costco, you are going to put a new pack of water right over here, right? So this is the operation that we're going to do. So we are going to first increase top by 1, and so it's like we move top from 4. Let me use a different color. We move top from the place of 4 to 5. So we have top right to point to 5, and then we're going to assign x to the 5th place of the stack. So we just assign the new value 17 added. So that's the push that's the push operation. Okay. So here so and again, if we want to push a new element, let's say 3 into that, we first will increase top from 5 to 6, and then assign the new value into the corresponding space. Okay, so this is how we insert a new element into stack. And let's say how many operations did we perform in order to push a new value into the stack. if we look at the pseudocode, it's like two operations. We have one operation that increase the value of top by 1, and then we just do a value assignment. So here we got two operations. Okay, so we'll keep that in mind, and I'm going to revisit the number of operations later. So then let's say, how do we delete an element from the stack? So the delete function for stack, the delete function has a special name called pop. Pop is like the delete the version of delete function for stack. So the pop function takes one input parameter s, which is the stack. So suppose here, okay, we have a stack. Here we have a stack right over here, and we have top equal to 6. And so how do we so delete an element? So before that, I want to ask you, which element are we going to remove? Remember that we do the last in first out policy, right? For stack, we have the last in first out policy. So which element comes last? It has to be the one that is pointed by top. So this element is going to be removed from the stack. How do we remove it efficiently? Some of you may say that we definitely need to like decrease top by 1, because say after we remove this element, after this element is crossed, so the last element is going to be right over here. So we need to decrease top by 1. But also some of you may think, okay, we need to like erase the value right over here. But how do you erase an element? Like suppose here, how do you so how do you erase an element from an array? There is no way. So the best thing that you can do is to override it with a new value. Let's say 0 by default to denote there is no value. But when some people say 0 over here, you may think, okay, if so there is an actual value, so it represents the value of an actual element. So actually we only need to decrease the value of top by 1, and that's what we do. And so this is because if we decrease top by 1 to 5, it lets us know that the stack, there are only 5 elements in the stack, and this here at this place, even though there is an element, it does not belong to the stack. Next time when we want to insert a new value, let's say we want to insert 17, then we will let 17 overwrite this place, so this value is ignored. Okay, so here for us to delete an element from stack, we only need to decrease top by 1, and then return as top plus 1. Here return as top plus 1 basically return the element that is removed. So it returns the value that has been removed. Okay, so it just returns the value that is removed. Okay, so this is what we do with pop. And actually this kind of philosophy is so by just decreasing the cursor or decreasing the index by 1, and without actually removing the value, is widely used in computer science. For example, so if you have a file in your file system and you want to delete that, so most of you would just right click the file and then so select delete or send it to the recycle bin. So do you know what your operating system will do? So previously we all know that so each folder has each folder so basically gives you a list of files included in that. We have file 1, file 2, so this is for folder. Okay, file 3. Suppose here you want to remove file 3. What it does is that it only removes file 3 from the folder itself, from the list of files, but actually the file still resides in your hard drive. The file actually exists, but it just say okay, it does not. Okay, so you can take the folder as an index of files. So basically, to only remove that index, but the actual file still resides on your hard drive. So this gives you an alert. So if you have a old desktop or laptop that you don't want to use anymore, do not just throw them away to the recycle bin or to the dustbin. No, so because or so even if you just say so want to you click the remove button on all those sensitive files, it will not help you, because if someone collect that hard drive, and he can easily restore the original files on your hard drive, because those files still reside on your hard drive. It's just the index does not exist. So there are some softwares to restore the index from the actual files, and then those people are able to get access to your sensitive files, and this is definitely very, very dangerous for if you have like your bank account password on your stored in your file. Okay, so instead, what you should do is that either you physically smash your hard drive, or what you can do is that you first delete that file. And then you first delete the file that you want to eliminate, and then next you should do what? You should keep downloading. So to let just download like random files, maybe some movies, maybe some like garbages, and so that you have the garbage overwrite the previous space that is occupied by your sensitive file. Okay, so this is the way to help you. You should do it multiple times to make sure that you don't have any corner case, and this is how you safely throw away a recharged laptop or desktop. Okay, so here let's look at the number of operations included in the pub function. So previously, when we learned counting sort, I told you that if we want to infer the complexity of a function, we need to pay attention to two parts. The first part is the function call, so whether it calls another function call. The second part is loops. Okay, here in pub function, we do have a function call. We call the empty function, by checking if it's empty or not. So let's go back to the empty function. How many operations are there? Just two operations. Let's say, so if it's true, we return so if this is top is 0, we return true. So we have one operation by checking if this is true or false, and then we have another one just to return either true and false. So in total, we got 2 operations. So here we got 2 operations, and then if it's true, we do one operation, that is to send out an arrow. Otherwise, we do 2 operations. We decrease the value of top by 1, and then we return the value that has been removed. So in total, in the worst case, we have 2 plus 2 operations equals to 4 operations. So okay, here let's look at this part. Okay, the complexity part. For the push function, we got 2 operations. For the pop function, we got 4 operations. So this means what? No matter how long is the stack, how many elements are there in the stack, the number of operations will remain constant, either 2 or 4 for these 2 functions. Okay, so that means this. Okay, so the complexity of, or the execution time remains flat regardless of the size of your stack. This is what we want. And for this kind of like constant time complexity, we use a term called O1. O1 denotes that the complexity, so 1 has nothing to do with n. It has nothing to do with n. It means that the the execution time is going to be irrelevant to the size of your input, and it's going to remain the same. Okay, so this is the operations for the stack, and we have push and pop. Both have O1 complexity. That is what I said over here. The time complexity of all the three functions are O1. Okay, so and a very famous application of stack is in calculator. So when you go to your senior year, when you take the course software engineering, I think some of you will choose to implement a calculator by yourself, and then at that time you are going to use stack. Okay, so next let's look at the second data structure, Q. So Q is pretty much stack, which also supports, let's look at here, which also supports very efficient insertion and deletion operations. But it organizes the data so that the insertion and deletion are very efficient. But so in terms of the policy, okay, so Q implements a last in first out policy. Okay, stack implements a last in first out policy, while Q implements a first in first out policy. So let me turn off my wife's social account so that it stops keeps sending alerts. I'm just going to go to right over here, log out. Okay, so she uses this too. Okay, and then and next let's look at here. Okay, the Q has two attributes. Q implements the first in first out policy. So let's see how does it implement that policy. So here Q has two policies, head and tail. Head points to the first element, or the head is the index of the first element, while tail is the index of the next location that is empty. So here, suppose say someday in the morning, we got so your doctor's waiting room has 12 chairs, and so far there are 11 patients who have arrived, and the first 6 patients have already gone to see the doctor. So from the remaining ones, the first one that comes to the waiting room is the value 15, whose index is 7. So that's why we have head equals to 7, because head is the index of the first element. And then the next available space, if a new patient comes, the new patient has to wait after the last patient in the waiting list. And that is so the last, so tail points to the next available place. So here we have tail equals to 12, and so if a new patient comes or a new value comes, it's going to reset here. Okay, so here, so different from stack, which only has a single variable named top. In Q we have 2 variables, head and tail, which is the index of the first element and the index of the next available position. Okay, so here is how can you check if the queue is empty or not, and so here we need to learn 2 functions for queue. Basically, these 2 functions help us to do insertion and deletion. So for queue, we give insertion function a name named Incube, but actually we can take it as insert. So it takes 2 parameters, q and x. Q is a queue, and x is the new value to be inserted in. So for example, right over here we have a queue in figure A, and so if we have a new element 17 to be inserted in Q, we need to put 17 right over here, and then next we will need to change the value of tail because this place is no longer available. So first we are going to assign the new value into the position of tail, pointed by tail, and then we're going to change the value of tail. So suppose here, okay, in the patient's waiting room, the chairs from number 7 to number 12 have been occupied. So if a new patient comes, where should the patient stay? The first answer is that the patient should stay out of the waiting room, no matter how cold or hot it is outside. Or we can let the new patient occupy the first place, occupy the first position. But we just keep a note, okay, saying that everybody just keep a note that the first, even though this new patient sits at the first place, the patient actually who comes to the waiting room is 15. So okay, I think most people would choose the second one, right? So yes, that is what we do. So after we let the new value 17 reside in a position pointed by tail, we are going to move tail to here. We have tail equal to 1. So which means that if we have a new value comes in, the new value will reset here. So suppose here we have a new value 3 comes, another 3 comes, and then we'll move 3 over here, and we'll let 3 stay here, and then next we'll just increase tail by 1, so which points to the next available space. So this is how we do. We basically recycle the available spaces in a circular way. So which is, and this is more efficient. Okay, and so this is the pseudocode for the incube function. First so what we do is that first we let the new value reside in a space pointed by tail, and then we just change the value of tail. If tail is the same as the length of the array, then we will just like make it 1, like what we discussed right over here. When tail is 12, we just give it a new value 1. Otherwise, we just increase the value of tail by 1. Okay, fairly simple, right? So here, let's check how many operations did we perform. We got 1 operation over here, 1 operation in the if. So if it is true, we have 1 operation. Otherwise, we have another operation. So it's like we have 2 plus 1 operations. In total, we got 3 operations for the incube function. Then let's look at the decube function. So for the decube function, so decube is pretty much like delete. So here, if we want to delete a value from queue, by the way, if we delete a value from the queue, we also want to return the value. Okay, so here, so let's say we have a queue on top of that over here, and if we want to remove an element, which one are we going to remove? Remember, queue implements a first in, first out policy. Who comes to the queue first? The value that is pointed by head. So we're going to remove 15 from that. Okay, so after we remove 15, we will need to increase the value of head by 1. So head goes to here. Head goes to here because when 15 goes out, the next in all the remaining elements, 6 is the first one that comes, and its index is 8. So that's why after that we'll set head as 8. So these are the operations in the decube function. First, we assign the value that is going to be removed from the queue. Okay, and we assign the value to x, and then if head is equal to the length, like what we did before, if all these values are gone, and then we have head over here, and after we remove this element, then the first element in the array will be 3. Okay, so that's why we're going to set head equal to 1. Otherwise, we just increase head by 1. Okay, so and then finally we return the value that has been removed. Okay, so these are the operations. Again, let's count how many operations did we do. We got 1 operation over here, 1 operation in the if condition, Next, if it's true, we are going to perform this one operation, and then otherwise we'll perform this operation. Finally, we are going to return. So it's like the number of operations that we're going to perform is 4. Okay, we got 4 operations. Again, if we look at the number of operations in the Incube and Decube function for Q is constant. 3 and 4 is irrelevant to the number of elements in a Q. So they give us, both of them give us O1 complexity. Okay, so this is the Q. Q is widely applied in operating systems. Let's put it in this way. Okay, so suppose here you are running a laptop. Let's say, how many CPUs do you have? Normally now, so we only have 1 CPU, and for those more powerful computers, we can have 4 CPUs at most. But for average usage, just let's make things easier. Suppose here we only have 1 CPU, a single CPU, and if you know that CPU is for what is the short name for what? Central Processing Unit. This is like every command or every line of your code has to be executed by the CPU. That is the hardware that actually runs the program for us. So okay, and let's say we only have 1 CPU, but how many applications are running at the same time? Let's say nowadays we are used to listening to music, and then so browsing websites at the same time. So you got your web browsers, you got your Spotify, and then you got your Word file opened, just to pretend that you are studying. I'm just at least that what I was doing when I was an undergraduate student. Like when I was in class, I think from the senior year we are allowed to bring laptops to the class. So every one of us just opened like a Word file in order to, if the instructor checks what we are doing, we at least we have something to show. And then everybody is running a browser or a game in the backend, so we just switch between these tasks if the instructor stepped down to check what we are doing. So like, and then you got some other applications like Notepad, a lot of them, and also you got your, I don't remember that software for messaging. What's that? WhatsApp. Yes, WhatsApp. I rarely use that, WhatsApp. And then you have your TikTok. So let's say we're running 10 applications, but remember, you only have a single CPU that is able to actually run commands, run your program, but you are running 10 applications at the same time. So how could that a single CPU manage to run 10 programs at the same time? So this is because our operating system organizes the CPU in a very smart way. So first, it creates a waiting list of process to run. Okay, it's a waiting list. We call it a ready list. Actually, in computer science, in operating system, it's called a ready list. So ready list, so which are a list of processes or applications that are ready to be run. Let's say we have A, B, C, D, E, F. And then we have a single CPU. So every time the first one that is in the ready list is going to be able to go to the CPU to run, but for a very short amount of time, at most 2 milliseconds. Okay, because our CPU is very fast. Okay, so if it runs the application for 2 milliseconds, it's good enough. And then next it will say kick this process out, and then move the process to the end of the waiting list, and then the CPU will just go to run the second process, then third process. So it's basically, it creates a waiting list of processes that are ready to run, and So this is called a CPU scheduling algorithm, and the most basic version is called first come first serve. First comes first serve scheduling algorithm. So if I talk about first comes first serve, most of you can relate it to first in first out, right? Which is the policy implemented by Q, and actually that is so the first come first serve scheduling algorithm is based on Q. It basically organizes all the processes in a queue, okay, with the insertion and deletion operation, or incube and dequeue operation. Okay, so this is for stack and queue. And next I'm going to, so for stack and queue, you should read chapter 10.1 to have a good understanding. And next, let me talk about linked list. Okay, so I'm going to go over the third data structure that we're going to learn this week, that is linked list. Okay, before that, so I want to briefly talk about so the feedbacks that I have heard from you. Okay, so last week I think I received a lot of emails. I can find those emails on my phone, even though my laptops are down for 3 days. So I didn't reply all of them. I'm sorry about that, because some of the emails ask me to debug their programs. But as I don't have my laptops with me, I can't do that. I couldn't do that. But I will start replying you tomorrow morning. Okay. So what I say is that the most difficulty from the students are understanding the pseudocode, or kind of like understanding the difference between the index, because as I said, in a pseudocode it uses index starting from 1, while in Java we have the starting index is 0. There is a discrepancy between them. According to my previous experience, if you have such difficulty, so if you just, let's say, for one homework, if you I think like for most US students, they don't like reading the textbooks. Instead, they basically just want to go to the lecture and read the PowerPoint slides, and then go back to do the homework. So I think this is fine if you are doing literature, if you are majoring in literature or music or some other majors. But for computer science, at least for this course, that structure course, this is not sufficient at all. So if you, let's say, for one homework, you just spend, you're confused, you just translate the pseudocode from the program from pseudocode to Java, and then but you just realize that your code didn't work, and you spend, let's say, 3 hours on debugging and searching on internet for resources how to fix the problem. My suggestion is that, okay, why not that you do not spend those 3 hours on debugging, instead of spending 3 hours on debugging? Why not just spend 1.5 hours read the book before you start the homework? Okay, so after you go over my lecture, go to read the book, and then by combining my lecture and the textbook, you are going to have a much better understanding of the pseudocode. So you know, okay, this I is forward index, that J is forward index, that K is forward index. So you know, okay, how to adjust those values in your Java program, even though there is a discrepancy between the starting index. Okay, so that's my suggestion. Go to read the book first before you start the homework. It saves your time. And the other thing I want to talk about with you is that if you just spend 2 hours debugging, still you have no clue on how to find them, it's not a shame at all. This is absolutely normal. Okay, so in those scenarios, you should send an email to me. I'm going to fix the code for you. I think in the past 2 weeks, I replied around 20-25 students' emails, helping them fix the code, fix their programs. So the way that for me to fix the code is going to be relatively quick and simple. I'm going to just find out the problem in your code, fix it, and reply you with the code, and with a very short sentence say, called check my changes. Sorry, I just cannot explain why I make those changes in an email. It's too hard, right? So I probably will have to write for 20 minutes or 30 minutes for each program in an email, and that is way too long. So instead, I'm just going to reply one thing: check my changes. So after you receive my revised code, you should not just like, yeah, I got the correct code. Let me submit the code and get 100 point in my homework. Yeah, of course you can do that, but besides that, you should really check your code. You should really check the difference between my code and your code to find the very subtle changes that I made, and that is where you learn. And from there, you should try to understand why making those changes, subtle changes, help your code to run, and that is how you learn from programming, and that is also how I learned programming by myself. It's like you have to understand the logic from someone who is better at programming than you, so that you can improve your programming skills. Okay, so it's not a shame to ask for help, but after you get the help, check the help to say why those help works. Okay, so then let's look at the last data structure that we need to learn today. That is called linked list. So previously we learned stack and queue, and we said that they support efficient insertion and deletion with O1 complexity. But they are based on arrays, and the difference between stack and queue is that they implement different policy. Stack implements last in first out policy, and queue implements first in first out policy. But for linked list, it's going to be totally different. It's irrelevant to array at all. So for the first time, we're going to organize the values or data in a structure that is different from array. So in linked list, we store everything in. So let's look at so before that, let's look at the difference between linked list and array. For array, so if we create an array of this, okay, 1, 2, 3, 4, 5, 6. We create 6 space. So in our physical memory, in your memory or in your RAM, so this is the hardware that stores your program. So these 6 elements are going to be arranged in consecutive space, are going to reside in a consecutive space. So we have A1 equal to refers to the first element, A2 the second. So they just occupy consecutive space. But for linked list, it's not. So for linked list, what we do is that, so we have listed nodes. Each of them is a node, and each node includes a data field, like say what kind of value it stores, and also it has a link to the node next after that. So like over here. And okay, so these nodes are going to reside in different spaces in our memory. And then so this is node 1, node 2, node 3, and node 4. From the links inside this node, we will be able to know, okay, where is the next one, and then where is the next one. So this is how linked list works. So again, array stores the elements in consecutive memory space, but linked list stores the values in very sparse spaces, in discrete spaces. Okay, so there are 4 types of linked lists. So I'm not going to talk about the details of them, but instead I'm going to talk about what we are going to focus on. We're going to focus on double linked list. So in double linked list, so if you look at the files that the files or the skeleton code that I provide for you to do your homework for. For list, we have two parts. We have two files. The first one is called list node.java, and the second one is called LinkedList.java. LinkedList.java. Okay, let's first look at what is list node.java. So here, because we are learning, we're focusing on double linked list. A double linked list is like that. Every node right over here, every node has three fields. So has three fields. The key, which stores what we can take it as three variables. The key stores the actual value, and prev is short for previous. It stores the link to the previous node, and also it has a variable named next. It has the link to the next node, to the node after it. Okay, so that's why we have the three different elements. And actually, if you look at this list node.java file, I define a class named list node. This list node has three fields. The first one is just int key. The second one is list node the previous, and list node next. Okay, so this is exactly the same as what we learned over here. So each node has three elements. Okay, so that is the structure for, that is the definition for list node. And if you go over the Java review or Java tutorial slides, we call them what? You should know that we call them what? Member variables, class member variables. And also I define the constructors for the list node structure. And when you are doing your homework 4, you should leave list node.java untouched. And instead, you should just go to insert your code in list node.java. Sorry, LinkedList.java. Okay. So for linked list, so it only, let's say, let me just use a different example. Suppose that let's find it this way. Okay. Suppose that you know your parents' address. And you have the knowledge. You have the knowledge of your parents' address. Your parent. And your parent have the knowledge of your grandparents' address. Has the knowledge to your grandparents' address. Okay, suppose that I'm doing some work, social work. I want to find all of your family members. So if I only know your address, am I able to find your parents and your grandparents? The answer is yes. After I find you, I'll be able to ask you what's your parents' address, so that I can find your parents. From your parents, I can ask for your grandparents' address. Okay. So here, like only by knowing your address, I will be able to find all of your relatives. Same here. Okay, because in linked list, each node includes a link to the next node. So we only need to know the first node. If we only know the first node, we'll be able to go through all the nodes in the list. And that's why in linked list.java we only have a single member variable that is called, whose type is list node, and we call it head. Okay, which is like the first node. Head is the first node in the list. And if head equals to nil, or if nil in Java, nil means, so here nil is like now in Java, means empty or nothing. Okay, if head is nil, it's the keyword for empty or nothing. If the head is nil, it means that the linked list is empty, there is nothing. Okay, so next, let's look at the functions for linked list. So here, if we want to search for an element in a linked list, L is a linked list, and K is the value that we want to search for. K is an integer that stores the value that we want to search for. We basically want to search if in a linked list, if there is if it stores the value. So let's look at this linked list. We have L, and we only know the head of L. The head of L is right over here, and then we have K. Let's say we have K equal to 4. We want to search for the value 4. So initially we start at the head. We start at the head, and so we check if so here we have X. Okay. Okay. So initially we have X equal to head, X equal to the head of the linked list. First, we check if X dot key is the same as 4. X dot key is 9, and it's not 4. So we're going to move X to the next one. We're going to move X to the next node, and then we are going to compare its key with the value of K. It's not the same, so we're going to move X right over here. Yes, we find so the key of X is 4, the same as K that we want to search for. So we basically stop the search, and then we return X. We actually return the node that includes the value that we want to search for, and this is the search function for linked list. So first we have X as the head, while X is not nil and X is not the key stored in X is not the same as K. It moves X to the next one, to the next node, and if this two conditions, one of these two conditions are not satisfied, it just return X. Okay. So the search complexity of this algorithm is going to be O(n). This is because in the worst case, we're going to go over every node in the linked list to find the value that we want to search for. If we have n nodes, then we're going to have to visit n nodes. Okay, so that's why we have O(n) complexity for search. But next, let's look at insertion. So here for insertion, we always want to, if we want to insert a node here, the insertion function takes two parameters, L, which is the linked list, and X is the a new node to be inserted. So here, let's say we have a new node X. In this example, we have a new node X, and which stores the value 25, and then this is neo, and so its previous and next field are both neo, so it only stores a key and 25. We want to insert this node into the linked list over here, and by default we always want to insert the new node into the beginning of the linked list. So what it does is that, okay, first it says x.next equal to l.head. So it's like it builds a, let me go over this example with more clearly. Okay, so we have the node X, it stores the value 25. Originally both its previous and the next field are new or now for Java. Okay, so first we have x.next equal to l.head. L.head is the first node, so it first builds a link from this node, from X to the head. And then if l.head is not neo, yes, obviously it's not neo, then we need to execute the next line. L.head.previous equal to X. So just set a link from l.head to X. Okay, and then it says l.head equal to X. So here it say now we have a new head. L.head is at here, is at X, and we just in the last line we said x.previous equal to new. Originally it's new, so this makes no change. So after that will have something like this. Okay, head points to x, which is the new node, and after that x has a link to the original first node, which stores the value 9. So this is the way we insert a new node into the linked list. And so here let's look at the number of operations that we perform. We got one operation in the if condition, and if true we have one more condition, one more operation, and one operation. In total we have 5 operations. Okay, so then let's look at the deletion function. In my opinion, this deletion function is really beautiful. So the deletion function again takes 2 input parameters, x, l and x. L is the linked list, and x is the node to be removed. So here we have x equal to this node. So basically we want to remove this node from the linked list. So let's look at what it does. If x dot previous is not new, x dot previous, this is x dot previous. X dot previous is here, okay, points to here, and x dot is not new, so we need to execute this line. X dot previous dot next equal to x dot next. This is x dot next. So it will set x dot previous dot next equal to x. So here it just cross out this link, and so this link is removed and reset to as here, okay. And next else l dot head is x dot head equal to x dot next. Here we don't have, so we don't need to execute this line because the if condition is true. And if x dot next is not new, here x dot next is not new. We set x dot new dot next dot previous equal to x dot previous. Okay, so we just like remove this link and reset this link in this way. We just overwrite this link in this way. So here actually what we got is that if we traverse the linked list from beginning to the end, we're going to start from the first node to this node, into this node, and then all the way go across to the last node. And from the last node, if we go back to the beginning, we'll go to the node with the value 16 and sorry. Yes, and then go over here and then go over here. Okay, so you can see that this node x still exists, but it is totally skipped from the list. So it's like we let the node to be deleted exist, but we just exclude it from the linked list. Okay, so then let's look at the number of operations in the deletion function for linked list. We have one operation in the if condition. If it's true, we got one operation. Otherwise, we got another operation, and if this is not true, we got one operation. So in total, we got 4 operations. So again, so here as we can see that the insertion and deletion function of linked list. So for these 2 functions, the complexity is irrelevant to how many nodes are there in the linked list. So we are safe to claim that they give us O1 complexity. That is what we want. But for search, linked list also supports search, but the search complexity is going to be higher. It's O(n). It can be linear to the number of nodes in the linked list. Okay, so yes, this is what we learned today. And so for linked list, please read this just 3 pages. After reading them, you will have a very good understanding. Okay, and also you will have homework 4. Since I upload this video late, if you need an extension with homework 4, feel free to send me an email so that I can extend it for you. And if I receive multiple emails, I will just extend homework 4 for everyone in the class. And so that's our video lecture for this week. And